So now we get to a real-world application of the cross product in the form of the physical quantity torque. So torque is what takes place when you have a place where you're going to create a pivot, a rotation of sorts. From this point, we're going to go out a certain distance. We're going to refer to that as R, because if we're going to be creating a rotation with this thing, then the terminal point of this vector is going to be sweeping out a circle. Now with that in mind, let's say that we go to the end of this thing, typically something like a wrench, screwdriver, something along those lines, and we apply a force. So what should take place is that your solid object, like a wrench here, then rotates, and the physical quantity that gets created from that is referred to as a torque. Now, with that in mind, you've probably heard the old adage, righty, tighty, lefty, loosey. Screws are designed in exactly that way to go with the natural torque that is associated with this. So in this case, this would be a righty-tighty. However, when we consider what's actually going on with these two vectors, we would need to replace F so that its initial point is at the same place as this. Now, torque is defined as a vector quantity, and in order to ensure that the right-hand rule is taking place, this is a righty-tighty case, so we would want the, well, this is kind of difficult to do, but essentially we would want the result going in the downward direction. If I do this with my fingers, that lets me know that R would have to be the first vector and F would have to be the second vector. This is way less awkward when we're actually doing it face-to-face, so it's a bummer that we're not. Now, with that in mind, since we are once again multiplying a displacement times a force, we are going to see something like joules or foot-pounds associated with this. Now, frequently we talk about the magnitude of the torque, and because we're going to be talking about real-world situations, keeping in mind the magnitude of the cross-product formula will be key. Now here's the thing though, when we talk about the angle in between the vectors, we're actually talking about this angle right here, not this angle over here, though that is typically how something like this would be depicted. The good news is that these two angles would be supplementary. They add up to 180 degrees. And the note that I'm going to make here is that if we take the sine of an angle and the sine of its supplementary angle, we do wind up getting the same thing. So chances are pretty good you could get a correct answer for a very incorrect reason. So just wanted to throw that out there before we take a look at an example problem.